they have this kind of an architecture here where you have, many different kinds of data modalities all being encoded into a shared latent space, pass through some kind of a, you know, transformer backbone, and then the resulting outputs are decoded into task-specific outputs like, motion plans or predictions of other vehicles or objects, bounding box detections, etc. Now, while most architectures will look something like this, the way that they're actually trained or the tasks used to train them can be very different. And so there's quite a few choices that you have in terms of what data you use to train, the different low-level details about the model, and then the different tasks that you use for pre-training or for fine-tuning. And what we've seen in the field is there's kind of two emerging predominant candidates, I would say, in terms of archetypes for foundation models. So the first that I'm sure many are familiar with are multimodal LLMs, and these are exemplified by models like Gemini, GPT-4o, Lava in the academic space, etc. And what these models do is they use quite a vast variety of pre-training tasks and fine-tuning tasks, depending on the domain of interest, as well as, a lot of different data representations. For example, if it's text or images or any other kinds of data modalities. And because they're trained on such a wide variety of data, typically, most of the internet, if not other domain-specific modalities, they're able to have some what almost looks like common sense reasoning capability. And I'll show an example of what that looks like in the AV space. So here I'm showing a road in Mexico, which is this is on a mountainside, a little bit rural, away from cities. And if you're driving here, for example, on vacation, and you see these arrows on the road, it might be a little bit confusing as to what they're signaling. But when we actually asked a VLM in order to give us like, some guidance about what should we do in this scenario, it was actually able to look at this image and reference it with information that it knows about like Mexican traffic rules to come to the right conclusion that it's, what these arrows are indicating is that it's safe to change lanes in order for you and drive into the oncoming lane in order to get more visibility about the blind turn that's coming up. And so it's these kinds of tools, these kinds of models, because of their very broad training, are actually able to have these kind of very strong reasoning capabilities, which we are particularly excited about using in the AV domain. This was a work from our group in CVPR with the link below if you're interested. Now, another I would say prominent class of models that we've seen emerging in the past year or so are video generation models. So models like Sora or Gaia in the AV space or Stable Diffusion. These models typically just focus on image or video generation as their task, but there's quite a few different choices for backbone models. And what they're particularly what is particularly of interest in the AV space with models like these is that there's a great capability to use them not just to generate here you see in the Sora video below, not just to generate videos of driving, but actually to generate videos of driving as it is, as it would look like from the car itself. So here you can see these are examples actually of an NVIDIA model, which is able to generate multi-camera videos that actually look like they're being received by AV sensors. And you can see that there's kind of a geometric consistency across the cameras from a text prompt, all from a text prompt, which you can imagine could be useful for example, generating additional data for perception, which you otherwise may have not seen in your data set before. Now, we don't just have to do this for 3 cameras. As you know, cars typically have sensors all around them. And so we've even expanded this idea to 6 camera, 360 view video generation. And we're particularly excited about these results because, even without, any very hardcore terms for geometric consistency, we're still able to, observe results like these. Now, it's not like everything is perfect and working correctly. The typical annoyance with video generation models is they suffer from hallucinations, right? You saw this kind of bike here in the bottom video materialize out of nowhere and then, disappear again. So still a long way to go. But the way that the group has been thinking about these two, dominant paradigms of multimodal LLMs and video generation is that while one has really broad knowledge and ideally common sense reasoning, video generation has this really keen ability to model the world surrounding an AV. And so our hope is that in the future, we're able to develop both of them towards a unified shared architecture, for example, maybe via a shared latent space, so we can leverage the strengths of both. Now, let's say we do have an AV foundation model in hand. As I said, one of the big things I want to discuss today is how we can actually use them to empower AV development. And I'll start with offline processes like auto labeling or simulation. So earlier this year, at iClear 2024, our group presented a work called Nerf that is able to, in a self-supervised manner, decompose and model dynamic driving scenes. When I say decompose here, I'm referring to the fact that it's able to, purely from self-supervision, segment out dynamic moving objects and then the static background. And not just that, but it's also able to give you the flow across time for those dynamic objects. And so you're able to see results like what's shown here. Now, this work was based on Nerfs, which means you're able to do a lot of very Nerf-like things, so to speak, which means, if you have some original camera log of a scenario, you're able to then move the camera around and do some novel view synthesis. Or because it's a Nerf and you actually can also query for 3D points, you're able to do, for example, LiDAR resimulation and maybe change the beam spread or distance or something like that. Now, a really powerful feature of this work that we learned was that in normal Nerfs, you have a reconstruction target, which is to generate to reconstruct the RGB image that you observed of the scene. However, you don't just have to use RGB as your reconstruction target. You can use, for example, foundation model features. And what this really allows you to do in a novel sense is that you're not able to bring these foundation model features into the 4D space of this Nerf, and that gives you some really interesting capabilities like auto labeling right out of the box. So for example, on the bottom left, we trained to reconstruct clip features. And what we're able to do is once we have a Nerf with these clip features in its feature space, we can query, for example, for literally the language car or traffic light or sidewalk or et cetera. And we're able to see which regions of the image or which regions of the 4D space light up. And so out of the box, you immediately get an auto labeling tool. And I'm going to show you here. This is what happens if you lift Dino V2 features into 4D, and you can actually see how you can even label them in 3D space across time, or at least how you get this feature clustering for different kinds of objects. Now, this approach has two important caveats that the group has been working quite hard to remove since this work was published. So the first is that Nerfs and Gaussian splatting and methods like these, they typically require per scene optimization. That means that you have to have your whole video that you've captured ahead of time, and then you can reconstruct that, and then you can do all of this auto labeling and everything just for that specific scene. And if you have a new scene, you have to do it all again. And then the second is any dynamic agents that you see in this video, they're all just being replayed. There's no reactions or anything like that if you were to try and use this as a simulator. So one thing I'm very happy to present is a new work from the group, which is going to be presented at NeurIPS at the end of the year, which is an approach to actually remove the need for per scene optimization. So what this work does is it, rather than using Nerfs as the core information representation, it actually uses a slightly more explicit 3D volumetric representation, and that is sparse hierarchical voxels, which nicely can be generated in a feed-forward manner directly from sensor representations and can then be trained using the same differentiable rendering techniques that we used in Nerf, or that you typically use in Nerf, Gaussian splatting, etc. Importantly, this method can also be trained using any per scene optimized nerfs that you already have. If you already did some project before and you have a lot of this data lying around, you'd actually use those for supervision. And what's really nice about that is when you train, when you train this model to reconstruct all those different variety of outputs, like foundation model features or just the RGBs themselves, you're actually able to get a wide variety of output modalities from the model as you already had them before. But now you can do this in a feed-forward manner. And because you are, in essence, distilling from multiple different scenes, this model is actually able to filter out any little artifacts that you typically see when you have a per scene optimized nerf. Now, it might be difficult to see over the network here, but if you look at the paper basically and the website and you see these videos, you'll see kind of the details being more accurate in the distill nerf rendered depth compared to other methods, even compared to Emmer nerf. Now, while that handles the first caveat, there's still the second caveat of all the dynamic agents being just replay. And so, thankfully, our group has done quite a lot of work in actually traffic modeling. And so, we have some knowledge about how to control agents and how to generate realistic scenes with simulated agents. However, even so, it's actually quite difficult and very labor intensive to initialize scenes, to generate scenarios, even if you know exactly what you want to simulate. And so earlier in the year, late last year, our group was working on enabling users to specify text descriptions of scenes and then have those be used to generate scenarios with generated trajectories for different agents. And in particular, I'm showing the results of what happens if you, rather than just taking text in to edit a scenario like on top, what happens if you take in text from, for example, a crash report, which is otherwise a very rare scenario, something that you might not see in collected data, and use that to generate scenarios. And I'm showing on the bottom here in this set of three, I'm showing text prompts, or at least a snippet of text from actual US crash report data collected by the government. And I'm showing the results of, if we pass this through our work LCT-Gen, in order to generate the positions of agents, retrieve a map that closely matches the text prompt, and then generate motions of agents within that scene, you're able to see that actually it's able to capture some of the nuances of this crash and actually recreate it in a simulated sense. These videos specifically were rendered in DriveSim, which is NVIDIA's commercial driving simulator. So that's why they look like this. Now, while I'm very happy about this capability to use language to actually generate scenarios, the difficulty is language is a little bit finicky if you want to generate very specific details, right? If you want a car at a specific position, if you want a car to move or a pedestrian to move in a very specific manner, text is a little bit too can be a bit abstract, and actually there's room for interpretation, which means the model might simply generate something else which is similar enough to what you asked for, but it can be a little bit finicky to provide specific details. And so what the group is going to be presenting at this coming Choral is an advancement of that idea, and I'll show you an architecture diagram and how we do this. But what it allows you to do is, rather than just providing, just being able to provide text in order to condition a scenario, now you can provide a variety of different prompts. So for example, you can provide explicit goal points for agents to go to. You can roughly sketch a trajectory for an agent to follow, or you can just, you can provide a categorical action for a specific agent, like, that it should decelerate, or that it should park, or that it should accelerate, or something like that. And what that means is that even from all the exact same scenarios, generated scenario on the very left, you can see there's very many different rollouts you can get based on the different prompts you can give. And what's important is the way that we do this is very general, and it uses a lot of the exact same machinery that we were already using in LCT-Gen, but with two important additions. So the first is, after we encode all the map and states of any initial agents that you may already have, or if you don't have any, then just encoding the map, the generator that we're using now, rather than just encoding text like we did in LCT Gen, we're now encoding multiple different kinds of prompts, right? Goals, sketches, actions, like I mentioned. And in particular, this generator, which is a transformer-based model that's able to, attend all of these different prompts to agent queries, the output of this generator is not just trajectories like they were in LCT Gen, but it's actually tokens that are decoded into policies. The important thing being that these policies can then be executed in closed loop, which means that these agents are not actually, when you see them driving in those generated videos, they're actually reacting to each other. It's actually executing in a closed loop manner. So they're actually able to see, like a little a snippet of the environment around them and then actually react to that as time goes on. So not only is this increasing the ease of which users can actually interact with simulations, but it's also still maintaining and actually advancing the ability to have closed loop reactive simulations. Now, where we're going with this capability is to, be able to combine sensor simulation, like I showed earlier, and traffic agent motion simulation. And so in particular, what we're really looking to enable is, so on the top here, I'm showing an example just from the Waymo data set. This is just a car coming up to a stop sign, and then a car on the left is also coming up to the stop sign and driving forward. And you can see in the original video, nothing too surprising. It just goes through. In the bottom video, we've edited a little bit what actually happens in this scenario. So I don't know if this will show up well in the due to the network, but on the bottom video, we've now edited that car on the left to drive completely through the intersection, to kind of ignore the stop sign and just drive completely through. And we're able to do this because, we're able to resimulate what the sensor observations would be with that vehicle moving through, and we're able to get the trajectory because we have this capability to generate new motions for existing agents. So, this is early days, but this is exactly the kind of simulation capability we really want to enable in general to further autonomous vehicle development, especially for rare scenarios that you might not see every day in collected sensor data. Now, moving on to the on-vehicle AV stack. Earlier in the year, our group presented a work called Paradrive, which what it did was it conducted a very large set of experiments in moving different blocks of AV stacks around and connecting them in different ways, and all towards the goal of finding what is kind of the best configuration of AV stack modules. What are the best set of representations of information that you pass between these modules? And we did this all in kind of like a directed graph optimization framework. And what we found, interestingly enough, was that actually this kind of an architecture that you see here, I'll call it like a parallel style architecture where you have sensors being featurized and embedded, and then multiple different decoding heads all attending to those same features, actually yields the best performance in terms of driving behavior, in terms of also the different output head accuracies. And what's interesting is that with this kind of an architecture, you can train all of these components at the same time, so that your latent space is actually learning from all of these different from all these different tasks. But at runtime, you don't have to run them all at the same frequency. So of course, motion planning, you're probably going to run at the highest frequency you can, at sensor frequency. But mapping, motion prediction, occupancy prediction, these can now be run at different frequencies, and you can actually free up some computational overheads in order to reduce the power that you need, for example, or to increase the rate at which you can produce motion plans or motion predictions, etc. And we found that the performance in terms of, for example, the collision rate or the accuracy of generated motion compared to the ground truth is state of the art. It matches or exceeds prior approaches while, as I said, maintaining a faster inference speed. And what we've done since this work earlier this year is we've kind of scaled up this approach a bit. So we've looked at combining techniques from foundation model design, like having very general pre-training tasks, such as video generation via next token prediction, as well as maintaining still the existing AV tasks like object detection or motion planning. And rather than just kind of a small, let's say, Q-former style transformer, we kind of scaled up the backbone as well in order to, to have this kind of autoregressive encoding and decoding capability. And what we've done, we've trained this model on internal data, and then we've actually deployed it in simulated scenarios in order to see if this kind of an archetype of design can actually drive without, many hand-coded guardrails or anything like that. And what I'm showing here is exactly this stack actually driving in a Nerf reconstruction of an urban scenario here in the California Bay Area. I'm showing the same thing on the bottom here, except the vehicle here is now doing a left turn. And while these are, of course, I would argue pretty simple driving scenarios, the fact that such a stack trained just on AV data with just these kinds of simple losses, or at least with AV task losses, is able to achieve somewhat reasonable driving performance is particularly exciting for us. So, definitely keep an eye out. We'll be, continuing to work on this and definitely keep an eye out on any advancements coming in the future. Now, one thing that is, as I mentioned, a bit of a caveat when it comes to doing simulation with reconstructed environments, besides the problems of what I mentioned earlier, for example, that you have to have all the data and that there's a question of replay agents. The other thing is that you can only reconstruct data that you've already collected data for, which means if, for example, I wanted to see how this stack would perform, I don't know, on Japanese roads or in Turkey or in Spain, if I don't have collected data there, it's very difficult for me to actually do this kind of evaluation and this kind of closed loop testing. And so something else that the group has very recently released, and it's actually still under review now, although I think I'm fairly certain the paper is actually up publicly. But what we've done is we've looked at ways to leverage the generation capability of video generation models while mitigating their hallucinations by using neural rendering techniques. And so in particular, what I'm referring to is, if we want to reconstruct or maybe enable us to use scenarios from different countries that we might not have data for, what we do in this work called Dream Drive is we start first with just a street view image of the scenario of like a, urban street level view of a scenario. And then we actually pass this through a video diffusion model in order to kind of, let's say, generate what a driving video might look like from that particular scene. And then we use this video to, along with a Gaussian splatting based 3D reconstruction model in order to now come up with a 3D reconstruction of that scenario. Finally, once we have this 3D reconstruction of that scenario, which we can then also use to filter out hallucinations, for example, floating artifacts or weird, objects that appear and disappear quickly, we're then able to render new videos actually moving within that scenario. And the important thing is here, I mean, yes, beyond just like rendering videos of kind of static scenarios with geometric consistency, we can also, for example, render videos with moving objects. Like here in this video on the top right, you can see that actually some of those vehicles by the video diffusion model were actually animated to move forward, and then the rest of our spatial temporal reconstruction pipeline was able to bring those into the 3D scenario that we're simulating and then re-rendered here into this video. So this, while this is, of course, just kind of a first work in the space, and it's not able to generate, let's say, tens of seconds or 20 seconds long videos, it's still an encouraging prospect for being able to generate data from anywhere in the world based on just very simple input data, literally just a street view image. Now, I'm going to briefly mention some of our thinkings about safety because I think, yeah, I want to make sure to leave time for questions and discussion. But the way that we think about safety in the group is we kind of have this three shell approach. So the first is, before we even start to do any work on using foundation models with driving, is at design time, right? We are thinking about, can we quantify any uncertainty that's coming from this model? Can we bring in any prior knowledge about, for example, traffic rules, or about the ideas that maybe, you want to avoid collisions or something like that, like very simple priors that we can embed into the design of the model. Then there's also what kinds of guardrails can we put in at runtime? So for example, how we might design runtime monitors, or how we might think of safety filters in terms of basically double checking the output of the model and making sure to remove or fall back to any kind of backup plans if whatever model we're using is not is not consistent between time steps, for example. And then the third is, let's say you developed a stack, let's say, you've trained it on lots of data and you're very interested to understand its performance envelope. We're also building, a strong sense of how you can verify and validate the performance of these stacks in simulation offline before you have to deploy it. So we're looking at safety KPIs, making sure that we can stress test models, making sure that we can capture the different kinds of operational design domains that we want to test, and make sure that we can, even expand that envelope a little bit more. And diving a bit deeper into how foundation models can help this. So whenever it comes to long tail robustness, whenever it comes to cases where there's kind of these semantic anomalies that are not really like a, let's say like a safety critical problem if we were behind the wheel driving, if the system interprets them in some way that it causes it to drive erratically, then that's kind of a safety critical scenario. And so where we think AV foundation models can really help with this is especially in these semantic anomalies where it's like, there's these traffic signs being carried on the back of a truck, or there's some, weird object, some distance away, or there's stop signs that have been, tampered with in a way that make them difficult to interpret. As humans, we might interpret them very easily. In typical traditional AV stacks, they might not be interpreted very easily. And so this is where something like a powerful foundation model can help us bring some of that common sense reasoning about these kinds of scenarios. The other thing is that, especially when it comes to reasoning about generalization or long tail events, it can be very difficult and very subjective to say what, for example, is good driving, or what, for example, is comfortable driving, or what, for example, is local driving to that region that you might not see elsewhere. And so this is also something where we're really excited about the prospect of using foundation models, which ideally have this kind of, have learned this kind of subjective reasoning that humans employ in order to, for example, auto-label or curate, specific examples of good driving, or to, for example, use them as potential value functions for what is comfortable driving, what is driving that is local to specific environments and maybe not in other environments. So kind of different axes of using foundation models in order to improve either the measurement of AV performance or their explicit safety on vehicle. And with that, I'm just going to wrap up overall with, I think foundation models, especially if they've emerged over the kind of the past 1 or 2 years, really bring us a new access to new capabilities that we haven't seen before, that I think can really, especially in the AV space, provide a leap in long tail generalization, in robustness, in understanding and leveraging human subjectivity for driving. And they can really empower the full AV program, not just auto labeling, not just simulation, not just the on-vehicle stack, but really everything in concert. And yeah, we in our group we've been looking at different architectures for doing this. We've kind of seen two predominant paradigms come up, and we've also seen different ways that we can leverage them in AV stacks. And so I think it's a really exciting time right now, and I'm really particularly motivated by the capabilities we've seen, and I hope we can kind of expand on these. And then finally, AV safety, even though it's kind of at it's the absolute underpinning of the entire field, the good news here is that foundation models, like other black box models, they're not magic. We have some strategies that we can use to confidently deploy them, and some strategies to even improve the safety of AVs using foundation models. So with that, I want to make sure we leave a good amount of time for questions and discussion.
Thank you very much, Boris. Um,